Future batteries keep smart devices charged 1,000 years. Energy storage units that can be charged from electricity and then slowly run out of energy throughout the day have become the beating heart of contemporary portable devices. Lithium-ion batteries have made a breakthrough in energy storage and transportation solutions from one place to another, and have paved the revolution in the electronic devices we use today. Sony was the first to introduce lithium-ion batteries for commercial use in 1991 when the company was looking for solutions to extend the life of its batteries used in video cameras. Lithium-ion batteries are now used to provide energy for many modern electronic devices, from smartphones and laptops to electric toothbrushes and portable vacuum cleaners. Last year, 3 scientists behind this revolutionary invention won the Nobel Prize for Chemistry. Depending on these batteries, we are expected to increase, as lithium-ion batteries are used in electric vehicles as an alternative to fossil fuels. And at a time when the share of renewables in the electricity supply around the world has increased, it is likely that we will need to produce massive amounts of batteries to store excess electricity to make up for the energy shortage in times when the wind does not blow or the sun does not shine. Currently, more than 7 billion lithium-ion batteries are sold worldwide, and this number is expected to increase to more than 15 billion batteries by 2027. But lithium-ion batteries are not without flaws, as they are able to maintain energy and store for long periods of time with frequent charging, and perform poorly when the weather is extremely hot or extremely cold. Concerns were also raised about the safety of these batteries and their impact on the environment. Lithium-ion batteries may burn or explode in certain conditions, and extraction of the minerals used to manufacture them may cause severe damage to the environment and societies. This has prompted scientists around the world to develop new types of batteries to avoid these defects. Some of them resorted to harnessing a range of new materials, ranging from diamonds to a kind of fruit that has an unbearable smell, in the hope of finding new solutions to provide energy for electronic devices in the future. Lithium-ion batteries work by allowing charged lithium ions to transfer electricity from one end to another through a conductive liquid solution known as an electrolyte. The lithium-ion batteries attracted attention due to the high energy density, that is, the maximum energy that the battery holds compared to its size, and the lithium-ion batteries have a higher energy density and a difference in voltage compared to the batteries available on the market. The batteries consist of 3 main components, the negative electrode and the positive electrode, and they have an electrical solution. The poles exchange turns. The anode, elevator, becomes the positive electrode and the cathode, is the negative electrode during the charging process, and vice versa during the discharge process. The cathode in lithium-ion batteries is made from a metal oxide with a metal. When charging, lithium ions and electrons travel from the cathode to the anode, where they are stored in the form of electrochemical energy, by a series of chemical reactions in the electrolyte, driven by electrical energy that flows from the charge circuit. When the battery is used, lithium ions flow in the opposite direction, that is, from the anode to the cathode through the electrolyte, while electrons flow through the electrical circuit of the device that the battery supplies. The materials that make up the cathode and the anode have changed over the years, which has improved the capacity of the lithium-ion batteries and energy density, and the cost of the batteries has decreased significantly compared to the past. Mauro Basta, a material scientist at Oxford University and supervisor of the second-stage lithium-ion batteries at Faraday, is looking to improve the energy density of lithium-ion batteries and increase their efficiency to avoid a decrease in frequency with charging. That is why Pasta focuses on replacing the flammable liquid electrolyte in lithium-ion batteries with a solid material made of porcelain. As the use of solid material contributes to reducing the risk of water solution ignition in the event of a short circuit, as happened in 2017, when Samsung withdrew 2.5 million Galaxy Note 7 devices after accidents in the batteries. Solid batteries may contribute to avert future combustion hazards, as it was discovered that the electrolytic solution made of polymer gel used in most portable electronic devices is also flammable. The solid battery allows the use of lithium metal instead of the graphite used to manufacture the anode, which contributes to a significant increase in the amount of energy stored by the battery. This will affect the efficiency of electric cars. As every electric car now contains the equivalent of 1,000 of the batteries used in iPhone phones, the use of solid batteries in electric cars will contribute to prolonging the journeys that these cars make before they run out of charge. And the demand for batteries will increase in the coming years to coincide with the shift towards electric transportation and the penetration of portable electronic devices in all aspects of our lives. Therefore, the search for alternatives to lithium may become necessary to alleviate its effects on the environment. The Lithium Triangle region, which includes parts of Argentina, Bolivia, and Chile, holds more than half of the global reserves of this mineral. But extracting it from salt flats requires massive amounts of water to purify lithium-rich salts and filter them to obtain pure lithium salt. In Chile, 1 million liters of water is used to produce 900 kilograms of lithium. Chile's environmental authorities have warned that the amounts of water used to extract minerals, especially lithium and copper in the region, exceed their rates of rain and ice compensation. Researchers at the Karlsruhe Institute of Technology are developing batteries using various anode elements, such as calcium or magnesium. Calcium is the fifth most abundant chemical in the Earth's crust, but research to improve battery performance with calcium is still in its infancy. Lithium is extracted from the vast salt flats in South America, but its extraction process consumes vast amounts of water. Reuters. Lithium is extracted from the vast salt flats in South America, but its extraction process consumes vast amounts of water. Research into the use of magnesium in batteries has shown promising results so far, especially in terms of energy density, and there are plans to put it for future commercial use. Some have searched for materials that do not require extraction, such as wood. Liangping Hu, director of the Center for Material Innovation at the University of Maryland, recently developed a battery using porous parts of wood to make electrodes, in which metal ions interact to generate electrical charges. These batteries are based on years of research on wood's energy storage capacities, including research on tin cellulose wood packaging. Because wood has a natural ability to absorb nutrients, these electrodes will store metal ions, and will not be exposed to swelling or shrinkage as is the case for the lithium-ion batteries. But batteries with wood and tin fibers are still under consideration, and Liangping team is looking to use them to charge their laptops in the future. These batteries lose their ability to hold the charge relatively quickly, as the prototype of these batteries retained only 61% of the storage capacity after 100 recharge cycles. Cobalt is also common in modern batteries, and is found in most batteries with lithium in the cathode. Cobalt extraction causes toxic gases that harm communities living near mines, as well as its negative impacts on the environment. Reports have revealed that children are used as workers in cobalt mines, especially in the Democratic Republic of the Congo, which hosts half of the world's cobalt mines. Apple, Tesla, and Microsoft have recently been sued for deaths caused by cobalt mining. This prompted Judy Lutkenhaus, a chemical engineer at Texas A&M University, to develop alternatives to lithium-ion batteries, using proteins, which are the complex molecules produced and used by living organisms. Anode is usually made from graphite, and the cathode is a metal oxide that contains elements such as cobalt. Lutkenhaus believes that these minerals can be replaced by organic materials. These batteries that depend on organic materials treat another environmental problem. In the event that lithium-ion batteries are disposed of in landfills, metals and electrical solutions may leak into the environment and cause double damage. It is estimated that only 5% of the lithium-ion batteries used in smartphones sold annually are recycled. Energy from fruits. A group of researchers is looking for new ways to save energy for mobile devices while tackling the food waste problem. Vincent Gomez, the University of Sydney chemist, and his team, converts the remnants of foul-smelling durian fruit and jackfruit, the world's largest, to supercapacitors that can charge mobile phones, tablets and laptops in minutes. Ultracapacitors are an alternative way to store energy. Super concentrates are usually made from exorbitant materials such as graphene, but the a.m.c team converts durian and jackfruit litter into a carbon aerobic gel, porous solids that are extremely light, with exceptional natural energy storage properties. The team heats the spongy pulp that is not eaten from that fruit, dries it with freezing, then puts it in an oven at a temperature exceeding 1500 degrees Celsius, then the team forms the porous light product into the electrodes of the ultra-low-cost capacitors. Supercapacitors can be charged in just 30 seconds and may be used to supply power to multiple devices, such as mobile phones. The team hopes that these supercapacitors will be used to store electricity generated from renewable sources to provide power for vehicles and homes. Before discovering these new uses of durian fruit, the odors of this foul-smelling fruit made headlines, with more than 70% of durian being dumped into the waste. The scent of its repellent waste disrupted the takeoff of a plane in Indonesia, and the evacuation of a library at the University of Canberra last year. Mikhail Istikhov, a physical chemist at the National University of Science and Technology in Moscow, conducted research to convert pork, an herb that contains a toxic juices that may cause burns and blisters on human skin, into a raw material for the manufacture of premium capacitors that can charge the phone. Batteries forever. Other researchers are working to address other problems with lithium-ion batteries, other than their environmental consequences. Tom Scott, a materials scientist at the University of Bristol, believes that lithium-ion batteries will be replaced by new energy storage methods in many contemporary uses, especially in extreme environments, over the next century. Scott and his team developed diamond batteries. The team developed a synthetic diamond containing the radioactive carbon-14 isotope, to obtain batteries that draw energy from radioactive isotopes, to produce a continuous current that lasts for thousands of years. When the radioisotopes inside the diamond crystals dissolve, they release high-energy electrons. These flowing electrons may be harnessed to produce an electric current. The researchers say that radioactivity outside the battery remains at safe levels. The team developed a prototype of a diamond battery, using artificial diamonds, and researchers exposed it to radiation from the nickel-63 isotope, so that electrons would flow through the diamond. The researchers are working on developing a type of diamond battery using the carbon-14 isotope extracted from graphite blocks used in nuclear power plants. Scott and his colleagues hope that these batteries will provide a solution to the problem of nuclear waste after the nuclear power plants are out of service, by turning them into long-term batteries. While the performance of chemical batteries such as lithium-ion batteries is weak at high temperatures, diamond batteries operate efficiently in the most severe environments, where it is difficult to replace used batteries, such as in space, in the ocean floor or on the tops of volcanoes. It may be an ideal solution for satellites and automatic sensors, so as not to stop working. These batteries are very small, Scott says. Researchers have developed diamond batteries that generate a voltage of 1.8 volts, like conventional small batteries, and these batteries are rechargeable, but Scott says that charging requires a few hours to be placed inside the core of the reactor to reach the original efficiency. Thanks to the continuous current generated by the decay of radioactive material, these batteries produce electricity for thousands of years, as the carbon element's half-life, that is, when its radiant intensity is halved, is 5,730 years. These batteries will also not be expensive, although they are made of diamond. Scott expects that very long-life diamond batteries will circulate in our homes, perhaps in fire alarms, remote controls, or in medical devices, such as pacemakers or hearing aids, for the next decade or two. We may not need to replace the damaged batteries in the darkness fire alarm again.